The purpose of this video is to show you how to use Laplace transforms to solve both first and second order differential equations. A basic schematic of this process is shown in the diagram as follows. Typically, when we solve a differential equation, we take a very direct path. This might involve separation of variables, method of characteristic equations, or some other way like muck. In this case, where we have the differential equation y prime minus y equals 0, with initial condition y of 0 equals 1, for example, we can separate variables to get y of t equals e to t. However, there's a whole class of differential equations in which this direct method is either complicated or not possible. In such situations, the Laplace transform can provide an alternative method for finding a solution. The basic idea behind Laplace transforms is that instead of taking a direct route, we first take the Laplace transform of both sides of our differential equation to convert it to an algebraic equation for a new variable capital Y. We then solve this equation to obtain a formula for big Y, which we then invert back to get a formula for the desired solution little y to our differential equation. In order to complete this process, the first question we'll have to answer is the following. Suppose we know that the Laplace transform of a function little y of t is big Y of s. What is the Laplace transform of the derivative of y? We can answer this question by going back to the definition of the Laplace transform, which states that the Laplace transform of y prime of t should be an integral 0 to infinity of e to the negative st times y prime of t dt. If you look at this integral, we want to relate this back to the Laplace transform of y, which we can write off to the side as the integral 0 to infinity of e to the negative st times y of t dt. Comparing these two expressions, the problem is that in the bottom one, we have a derivative in our exponent. To get rid of this derivative, we're going to use integration by parts. Recall, in integration by parts, the idea is that you want to move the derivative from one function to the other using the reverse product rule. So in our case, the function we want to get rid of the derivative on is y prime of t. So we're going to take this as our dv and this as our u, which means our v is going to be y of t, and our du will be negative s e to the negative st. Substituting this in to the integral above, we get u times v, which is e to the negative st times y of t, evaluated at the limits of 0 and infinity, minus integral 0 to infinity of negative s e to the negative st times y of t dt. Now in this first integral, you'll note that if we assume that y of t does not grow faster than an exponential function, which may not always be valid, but would then be an assumption of the resulting theorem that we're going to derive, then notice that this first term will simplify to negative e to the negative s times 0 times y of 0. The second term, if I factor out an s, will result in s times an integral 0 to infinity of e to the negative st y of t dt, which we'll recognize as the Laplace transform of y of t. So, putting this all together, and of course using the fact that e to the 0 is 0, the result that we get is that the Laplace transform, that was extremely messy, I'm going to rewrite that one. The Laplace transform of y primed of t is equal to s times the Laplace transform of y of t minus y of 0. We can take this a step further and also derive a formula for the Laplace transform of y double prime. We don't need to go back to the integrals and use integration by parts. We can simply use the fact that the second derivative is the derivative of the first derivative. Therefore, applying the result that we just derived, this will simplify to the Laplace transform, s times the Laplace transform of y prime minus y primed of 0, replacing y with y prime in the previous formula. We can then iterate the previous formula and apply it to Laplace of y prime. And what results is now a nice formula which relates the Laplace transform of the second derivative to the Laplace transform of y itself, and involves both the initial position and the initial velocity. You can continue this trick and get formulas for the third derivative, etc., but we won't need those in this video. We are now armed with all the tools we need to start solving differential equations using Laplace transformations. On the right-hand side of this screen, you'll see a review of all the facts we're going to need, including the Laplace transforms for sine, cosine, and exponential functions, as well as the two formulas derived on the previous slide for the Laplace transform of y prime and y double prime. We'll start off by solving a first-order equation, y prime equals y, with initial conditions y of 0 equals 1. In all examples in which you use the Laplace transform to solve a differential equation, the first step is to take the Laplace transform of both sides of your given equation. In our example, that leads to the expression that Laplace transform of y prime equals Laplace transform of y. If we use the formulas that we derived on the previous slide, namely that Laplace of y prime is s Laplace of y minus y of 0, then the left side of this equation would simplify to s times the Laplace of y minus y of 0 equals Laplace of y. And because it gets sort of tedious to write this calligraphic L and the curly brackets everywhere, we're going to set big Y equal to the Laplace of little y, and then rewrite the above expression as s times y minus our initial condition, which in this case is just 1, equals y. And we now solve for big Y to obtain big Y equals 1 over minus 1. That doesn't look like a minus, that looks better. At this point, we have now an expression for the Laplace transform of little y, and the final step is to invert this and get an expression for little y, our desired solution. In order to do so, we're going to appeal to the formulas derived during class. In particular, we're going to look at the expression for the Laplace of an exponential. Looking at the right-hand side, 1 over s minus a, and comparing this back with what we derived in our problem, we can see that this formula applies with a equals 1, and therefore little y of t just ends up being e to the t. We're going to proceed similarly for our second order example. In particular, we're going to start by taking the Laplace transform of both sides, and then using linearity to pull out the negative sign. Now, appealing to our formula for the second derivative of the Laplace transform, the Laplace transform of the second derivative of y, we end up with s squared times big Y minus s y of 0 minus y primed of 0 equals negative y. Once again, if we solve this expression for big Y, and of course plug in our initial conditions, which in this case are 1 and 1, then we end up with s plus 1 over s squared plus 1. If we compare this result with our formulas from class, we can see that we have something which looks like a sum of the formulas for the Laplace of sine and the Laplace of cosine of t. So we need to take this one step further and break this up as s over s squared plus 1 over s squared plus 1. And then we can invert the first to get cosine of t and the second to get sine of t, resulting in our solution y of t equals cosine t plus sine t. The process we used in solving the two examples on the previous slide can in theory be applied to any first or second order constant coefficient differential equations, even if they're non-homogeneous. To get an idea of some of the complexities that can arise in this process, let's consider the generic second order equation my double prime plus gamma y prime plus ky equals g of t, where g of t is an external forcing. For simplicity, we'll assume that our initial position and our initial velocity are 0. And that's so that we obtain simplified formulas of our Laplace transforms for the first and second derivatives, which say that the Laplace transform of the second derivative of y is s squared times the Laplace transform of y, and the Laplace transform of the first derivative is just s times the Laplace transform of y. Applying these formulas and taking the Laplace transform of both sides of our differential equation yields the result that ms squared times big Y plus gamma s times big Y plus ky should equal g, where g is the Laplace transform of little g. If we solve this expression for big Y, as in our previous examples, we can easily do so to obtain that y is equal to g over ms squared plus gamma s plus k. The complexity comes in inverting this expression, and this complexity comes in two places. First of all, we can think of this resulting expression as a product of an h of s and a g of s, where h of s is 1 over ms squared plus gamma s plus k. So the first complexity comes in how do we invert the product of two Laplace transforms. It turns out that there's a whole set of results which are related to convolutions of functions which allow you to do so, and unfortunately we won't have time to get into that during this video or even this course. The second area where complexity arrives is in terms of factoring the denominator here so that we can recognize h of s as the Laplace transform of some known function. This is where some algebraic trickery often comes into play, where you have to use things like partial fractions and, going back even further, complete the square. You can see a couple examples of this in the book. However, we won't be doing any of them in class. I also want to point out that this h of s function down here plays an important role in control theory and other applications, and it is called the transfer function for this system. It's called the transfer function because it tells you how to relate an input, which in the Laplace domain is given by g of s, to the output y. In fact, you'll note that h of s is in fact the ratio of the output to the input, g of s. Also, looking at h of s should make two other whistles go off in your head. First of all, notice that the denominator here is exactly the characteristic equation we saw back in Module 2, with s replacing lambda. Second, if you replace s with I omega and take the modulus of the result, you'll note that the result is simply the frequency response function, which we also studied back in Module 2. So the transfer function, which comes from taking Laplace transforms of both sides of these equations, encodes both of these quantities, and therefore is as good a place as any to end our discussion of Laplace transforms.